Topology has.
Yell at everyone's audience.
Yes, hello. So it is my great pleasure to welcome Draw Bar-Natan to narrate his elaborate handout. Thank you.
Thank you very much. Indeed, I will narrate my elaborate handout. So my abstract, I hope you've already seen, and it appears somewhere on the big handout. The big handout. So I'm actually repeating a talk that I gave a month ago or so in Oaxaca, Mexico. And the talk was the handout, but today, since it's only 20 minutes, I'm only going to be talking about the part that's highlighted in green. So don't worry. However, if you want the full thing, there is a video at this URL, omega epsilon beta, and at omega epsilon beta /APAI, there is a paper. So you can read the full details. And maybe I'll start by something I learned from Vaughan Jones. So formulas stay, he told me one time, and theories and interpretations change with time. So I'll just state the formulas and that's it. So I'm going to tell you how to compute a lovely invariant, which I don't understand in some sense, of a knot. So first of all, you draw the knot in the plane, as on the right. So all crossings, in all the crossings, all the edges are pointing up. Of course, you can do it because you can always rotate them, right? And it's a long knot. You write it as a long knot. So at the bottom it starts pointing up, and at the end it ends pointing up. And you also label it with two labels. So every edge gets labeled with one label is a sequential label. So 1, 2, 3, 4, 5, 6, 7 in this case. And each label is also labeled with the rotation number of this edge. So each edge starts pointing up and end pointing up. So in between it could rotate a number of times, and you label it with the number of times it rotates counterclockwise. So for this edge it's 0, for this edge it's 0, for this edge it's 0, for all of them it's 0 except for edge number 4. And you define this rotation number for edge number k to be phi k. So phi 4 is -1 because edge number 4 starts pointing up, ends pointing up, but in between it does one rotation in the clockwise direction. So -1. And then you create a matrix as follows. So you start with the 2n plus 1 by 2n plus 1 identity matrix, and then for each crossing you add a block as follows. So first of all, there are two types of crossings, positive crossings and negative crossings, and in each case I will assume that the incoming up strand is labeled I, and the incoming down strand, lower strand is labeled J. So here it's Ij and here it's Ji, because the over strand is always I. And then the outgoing strands are I plus 1 and J plus 1. And then you'll add a block to the matrix A in row I and row J and column I plus 1 and column J plus 1. You'll add this matrix here, written here. Okay? And so, for example, and then you will define the matrix G to be the inverse of the matrix A. So that was A, and the G is the inverse. So for example, for the trefoil, you will be starting with the 7 by 7 identity matrix. These are the ones on the on the diagonal, sorry. And then for each crossing, so for example, for the yellow crossing, it's a crossing where I is 3 and J is 6. So in row 3 and row 6 and column 4 and column 7, I will be adding a copy of the matrix written here with the sign S equal to 1 because this is the positive trefoil, so it's a positive crossing. And likewise, the pink entries are dictated by the pink crossing, and the purple entries are determined by the purple crossings. I think it's clear, right? Do I even need to ask? I think there's just nothing here. So, okay? And then G is the green, I will sometimes call it the green function, and it's the inverse matrix of A, and here it is. Okay? And the Alexander polynomial of the knot is the determinant of the matrix A, slightly renormalized. So, I mean, if you want it to be the balanced Alexander polynomial, you have to renormalize it appropriately. Okay? So you basically multiply it by some power of t, and where the power is the total rotation number determined by the total rotation number, and the rise, the total signs. And if you are a classical topologist, you should be saying right now, this is boring, and you should yawn. So, I don't know. Hans, thank you. Because indeed, the matrix, I mean, the 2 by 2 blocks, you should recognize them from the Burard representation. The matrix A is a presentation matrix for the Alexander module of the knot, as computed by applying Fox calculus to the Wirtinger presentation. And the inverse is not quite the Blanchfield pairing, but it's related to the Blanchfield pairing. And all of these pictures are pictures from people so old that, you know, these are black and white pictures. So you should be owning. Okay? And here is where all the content is. Okay? So, for a crossing C, and remember that a crossing C is determined by a sign S and 2 integers I and J, you define R1 of C to be this formula here, of which I have nothing good to say except that it works, in terms of the matrix, of the entries of the matrix uppercase G. Well, it works, and maybe the one thing I will say is that it's quadratic in the entries of G. And then you define rho 1 to be the sum of R1 of C's over all the crossings of the knot, minus a correction term, so minus the sum over, so all the edges of the knot. For each edge you take its rotation number and multiply by another entry of the green function of the inverse matrix there. Now, since this was quadratic, it will have the, since this is quadratic in the inverse matrix will have denominators, the determinant, so the Alexander polynomial. And since this is quadratic, the denominators will be the Alexander polynomial squared. And so I multiply rho 1 by the Alexander polynomial squared just to clear the denominators. And then by direct stupid calculation, you can check that for the trefoil, you get this following polynomial as rho 1. And the theorem is that rho 1 is a knot invariant. And in Oaxaca, I said the proof is later. But since this is not Oaxaca, and I only have 20 minutes, the proof is not today. Anyway, if you are a classical topologist, now you should be saying, what the heck? What's going on here? Right? This is something that classical topologists don't do. Okay? You just never, well, I mean, it's so close to what classical topologists do. It was classical topologists' topology until the previous slide, and then this is completely new. Okay? Actually not completely new, because it relates to work by Rozansky and Overbay, and in Oaxaca I mentioned it, but at this time I skipped that, sorry. Okay. So your homework, and that's more or less the end of my talk, is to explain why it makes sense for a topologist to do a thing like that. What was going on here? Okay? But, well, it's still a 20-minute talk, and I used only 10 for the actual content, so I'll just say, well, it's not just an invariant, it's a strong invariant. So here is a comparison of the strength of the invariant with the Homfli polynomial, the Homfli PT polynomial with Chovanov homology. So just take these two together. and they attain 2,785 distinct values on the knots with up to 12 crossings, whereas this invariant attains 20, whatever it is, more. Okay, so it's stronger than stuff by these colorful people. It's also so-called homomorphic, and again, it's only a 20-minute talk, so I'm not explaining what it means, but basically homomorphic means has an extension to tangles, which is well behaved with respect to various tangle operations. And the point is that the moment you have an invariant which extends to tangles and is well behaved under these tangle operations, it has a chance of saying something about anything that can be defined using these tangle operations. And for example, knots of genus G can be defined using these operations, and also Ribot knots. And here is an example of how you define Ribot knots using these operations. So the invariant has a chance of saying something about Ribot knots. Okay? And in fact, it actually does say something about the genus. Okay? So it gives some genus bound, and sometimes it's better than the genus bound you get from the Alexander polynomial. Again, if I had more time, I would have told you that this green function has a lovely interpretation in terms of cars driving on the knot, and where you think of every crossing as an interchange, and occasionally, with some probability, cars drop from the upper layer of an interchange to the lower interchange, and then you place traffic counters in, and you measure the amount of traffic, and that's the green function. And then I would have told you, or this is this lovely theorem here, and then I would have told you that once you have this language, the actual proof of the theorem is nothing. So it's not a hard thing. And you know, if it was a hard thing, you'd expect it to not have an easy place. But since it's so easy, it must have a good place. But it still doesn't. That was your homework. Again, if I had more time, I would have told you that it comes from a messy thing in quantum algebra. So, you know, you look at cars and traffic counters and you realize that somehow they behave like the Heisenberg algebra, and you think, where did the Heisenberg algebra come from? And it comes from some other algebra and some limiting procedure, and that's how we came to this invariant. But again, I'm not saying all of this because it's a short talk. And I would have also told you, if it was a longer talk, that you can implement the invariant. The invariant is just nothing. So here's the implementation. You set A to be the 2n+1 identity matrix, and then for every crossing in rows ij and columns i+1, j+1, you add to the matrix the block matrix that I mentioned before. You compute delta, which is essentially the determinant, and G, which is essentially the inverse. You let rho 1 to be the sum of all R1s minus the correction term, where the R1s were defined already here. So it's basically, the program is just the definition, and it works, and it's absolutely nothing. Oh, and maybe I would have also told you, if I had time, that also computationally it's nothing, because all there is here in this computation is computing the determinant of a matrix and the inverse, but the determinant is the Alexander polynomial, and the determinant and the inverse are essentially the same computationally. So this is not much more than the Alexander polynomial, and after that there is a linear time computation, which is nothing. Okay? And again, if I had more time, I would have told you that there are generalizations which can also be implemented, and you can actually compute things. but I will not say any of these things because it's a short talk. Thank you.
So, who is the topologist responsible for this new invariant?
This invariant?
Yeah.
So no, it does not come from topology.
No.
So, I should have started, and in fact that was a sin. I should have started by saying that everything that I talked about is joint work with Roland van der Veen, and it continues work with by Rosansky and Overgate. Yeah, I really should have started it with that. That was sorry. I wanted to fit everything in the green, and I forgot that this is essential.
And so you mentioned some relation to the genus, a lower bound.
Yeah. So the degree of, wait, how does it go? The degree of row 1 is at most twice the genus of the knot, like the degree of the Alexander. So the degree of the Alexander is at most the genus of the knot. So this means that the degree of row 1, well, divided by 2, is a lower bound for the genus, and it is sometimes better than the lower bound that you get from the Alexander polynomial. So it actually has topological meaning. It seems to be a cousin of the Alexander polynomial, well, a friend of the Alexander polynomial, and then, you know, they play in the same places. But, yeah.
So, Dror, you're
The
not saying
understanding
it
is
detects
missing.
the genus, though?
Sorry?
It doesn't detect the genus. It's
No,
not.
it does not detect the genus. I don't know, yes?
Does it have any spatial form in the slice?
So we don't know yet. I mean, well, okay. So in fact, both slice knots and ribbon knots can be defined using the operations that this invariant is well behaved on. Again, I didn't define, so I have to just say well behaved on. Which means that there is a chance. It has a chance. They're not. It's not disjoint from the notion of ribbon and the notion of slice. So, you know, if you think of the Kaufman bracket, its definition just has nothing to do with the notions of ribbon and slice. So you don't really have a reason to expect behavior. But here the definition, like the invariant has properties that make it plausible that it will have good behavior on ribbon or slice knots. We don't know it yet. Yes?
Could you explain a little bit about the relationship with the colored Jones polynomial? And you mentioned here that dominated is not lesser, but
So,
how do we
and that's actually how Rosansky got to it. Well, in fact, by building on earlier work by myself and Garofalidis. So you expand the Jones polynomial, the color Jones polynomial, as a power series in 2 variables, and then it turns out that the coefficients make fill up only half of the plane. So basically, the 0 below some diagonal and are non-zero above the diagonal. And then along the diagonal, you can read the Alexander polynomial, more or less, the inverse of the Alexander polynomial with some substitution, but more or less the Alexander polynomial. And then row 1 is the term above the diagonal, the one diagonal above. Again, some substitution, some renormalizations. So if you knew the color-Jones polynomial, you could compute row 1. However, knowing the the color-Jones polynomial is a theory invariant, not a practice invariant. You can't compute it. You can compute it for a small class of for small knots or small special classes of knots, but in general, you have no idea how to compute it for all colors, because for this expansion you need all colors, not just 1 or 2 colors. So, so it's dominated by the color-Jones polynomial, but you can actually compute it. So,
Thank you.
yeah.
Is there any reason why this pair of invariants is like so much stronger than the Hongfly and Havana? Do you have any clue?
Luck.
Nice.
No, I don't know any. No.
I mean, I guess in that vein, is there a categorified version of it? I mean, it should be, right? Because you have a categorification of the color-Jones, you have a categorification of the Alexander polynomial. Can you categorify that diagonal, that I don't know.
So Mike Larson once told me when I was learning to juggle 4 balls after I've already learned to juggle 3 balls, that you should never learn to juggle 4 balls because everybody will ask you if you can juggle 5 balls.
Sorry. Sorry.
Sorry, Hans. So no. So so really there are 3 questions you could have asked. One is, does it have generalizations for other Lie algebras? 2, does it have generalizations going above the first diagonal, so second, third, and fourth diagonal? And 3, does it have a categorification? Okay, these are the 3 obvious generalizations that come to mind. And the answer is, well, these are the higher diagonals, and they're still polynomial time computable, but the polynomial gets worse and worse the farther away you get from the diagonal. And they're still homomorphic, they still have all the good properties, but the truth is that you can expect the best to come early. Like the absolute best not invariant is the Alexander polynomial. But that's all, so now we're doing the next, okay?
So there's some stabilization is what you're saying as you go up the diagonals?
Well, no,
or?
there is just, it becomes messier and messier and the benefits are less and less clear. Then the next question is, can you do more than SL2? And there is some preliminary work on that by Shaveling. And but there should be more, and we will do more sooner or later. And categorification is, I don't even know how to categorify the Alexander polynomial. I mean, yes, there are analytic ways to do it, but I don't believe that it will stay analysis forever. I mean, it will become at some point reasonable topology, and we're not there yet, so. Yes.
How much easier or harder is this to compute than other popular invariants?
It depends in what sense. So the size of the program is almost as short as it can be. The Jones polynomial can be written in a shorter program. As I mentioned, it's about the same as the Alexander polynomial. But in practice, a lot of work was done on Chovanov homology to try to make it better and better. And in fact, part of it is me. So in particular, the program was written way more carefully. So in fact, for knots with up to 100 crossings, this is comparable to Chovanov homology. But this is mostly because Chovanov homology has the advantage of time. Yeah. And probably if you go beyond that, then the computations of Chobanov homology grow like e to the square root of n, whereas this grows like, God, I can't say, polynomial, which is a lot less than e to the square root of n. The reason I can't say is because actually nobody knows how hard it is to invert a matrix of polynomials. It's known to be polynomial times, but the algorithms get better and better. So, but after that, after this matrix inversion, it's linear time. Well, sorry, linear number of ring operations where the ring is the ring of Laurent polynomials. Yes?
You started by saying you want to steer clear of interpretations, and now I'm going to steer you back. Do you have a working interpretation of row 1, or is it just a total mystery at this point?
Well, one interpretation is, well, it comes from quantum groups in the way of column number 2 of the handout. And that's basically it.
Oh. Thank you.
Well, I think it's a good time to thank the drawer again.